So that's figure 22.11, figure on top right hand side. So, and then on figure 22.10, you've got the different types of beam limiting devices, and that's kind of where the video from, was it Friday, left off, was with beam limiting devices, calculation of field size. So what you have is diaphragm. Just to review, those diaphragms are a fixed beam limiting device, and it's basically just a chunk of lead with a hole in it, and it's mounted generally to a piece of aluminum that slides into the collimator housing. And then you've got a cylinder, which is like a three-dimensional diaphragm, essentially. And the cylinder, just as the name would suggest, is cylindrical, right? It's a tube, and it extends. In most cases, all the ones I've ever seen were extension tubes. But there are cones, like what you're seeing in figure 22.12, and most of your old timers, if you run into somebody who's actually worked with these, will refer to both of those as cones. And that's kind of where if you had a tech tell you to cone down on something, use that for collimation? No? Okay, so if you're working with a really old tech, you may hear somebody say cone down, and that just means collimate. That's all it means. But the most common type of beam restricting devices are the aperture diaphragm, the variable aperture diaphragm, which is your collimators. And we've got two sets of collimators. The first set of collimators is really for limiting scatter radiation. So then you get into calculation of projected field size, and that's what you're looking at on 22.11. And with 22.11, you'll have questions that ask you to calculate the field size in two different dimensions, and we'll talk about that here in a minute. You see that in that example 22.11, assuming that our diaphragm in 22.10 was what they used for this calculation, is rectangular, right? So the examples that you might see and the test questions you might have would have like a rectangular type, sometimes have a rectangular type diaphragm that you would have to calculate your projected field size off of, which means you would have to work the problem twice, right? Once for length and once for width. If it's square, you would only have to work it once, but if it's rectangular, then you'd have to work it twice. So in that diagram, what it's showing is a single calculation. So what we've got is a distance from the focus, or from the X-ray tube, the emission, to the aperture diaphragm opening. That's your SOD. And you've got a SID, which you're familiar with, and that's the overall distance. And then you've got the size of the opening of the aperture and the projected field size. So generally, in those types of questions, what you're going to be given are your distance to the diaphragm, right? Your SOD, your SID, and you're going to be given the opening size, and you would have to calculate your projected field size, right? I don't think I've ever seen a question, I'm not saying you won't see one, but I don't think I've ever seen a question where you've been given the field size and had to calculate the opening size. Now, full disclosure, do you think you're ever going to have to do this in clinicals? And the answer is no. But with every education, you're going to learn some stuff, and you're going to have to be held accountable for knowing things that you're never going to use. It's called education. And I don't want to diminish the quality of education, but it is what it is. You know, I mean, how much time did you spend in school learning to diagram sentences? Do they still do that? Yeah. Sentence diagramming? Yeah. So how many times in the middle of a conversation have you ever stopped and said, wait, let me break down this sentence and figure out what all these individual words mean? Exactly none, right? Well, kind of same thing here. You're never going to have to do this, but it is testable on the registry as part of your education, so we have to know it, right? So the formula as it's set up on page 298 requires a lot of memorization, a lot of thinking, right? So if you had a chance to watch the video, you know, kind of walked through it and labeled it, relabeled it, renamed it something else. But let's just look at this thing. So you got SDD, and then you've got SID. Okay, so both of those are vertical measurements. Okay, so in those, what we're going to do is we're going to put those two measurements across the formula from each other. And if you look at the upper one, the top one, you see SDD is equal to SID, right? And those are both the denominators in this example. And the measurement of the opening and the field size are across from each other, okay? So in these type of problems where you've got something over something equals something over something, you got a lot of different variables and a lot of different ways that you can set it up. But as long as you keep the things that you're comparing across from each other, it really doesn't matter if they're here, or completely inverted, right? As long as the things are across from each other, because what we're going to eventually do is cross multiply, right? So if we cross multiply, it doesn't matter what's on top and what's on bottom, as long as the same things are on top and the same things are on bottom. It doesn't matter if you put one on one side or the other side, you're still going to be cross multiplying the exact same things, right? So it's what we refer to as a ratio type problem. And that's what this is it's, you know, something over something is equal to something comparable over something comparable, okay? So in this example, I'm going to kill the lights on one of these. Yeah, I got it right. All right. So what we have then, I bought some markers and I left them down in my office. Let's see if this thing has anything left in it. It does. All right. So what you may have is something that's a question that may say something to the effect of a 10 by 4 diaphragm is 5 inches below the target at a 40-inch SID. What is field size? So what you've got there is just go ahead and, you know, really on this particular test, if you have math, it's going to come straight out of DeAngelis. All right? So work your DeAngelis. In the spring, when we go back through this, you're going to get hammered pretty hard on tests with this. So you got to know it, right? But what I want you to know right now more than anything else is how to set it up so that when you get to it in the sophomore year, you don't mess it up, right? So what I recommend you do is go ahead and draw it out. So what you've got is an X-ray tube, and then you've got collimator housing, and then you've got some sort of diaphragm at a distance from your focus. So that says it's how far? That says it's how far? Yeah, help me out here. What does it say? Oh, come on, y'all. This is just reading. You don't have to know this. Just read it, right? What does it say? 5 inches. Thank you. It's 5 inches. All right. So then we've got an SID of how far? 40. There we go. So we got 40 inches. So then we've got a diaphragm. In this case, it's a rectangular diaphragm. And what does it say it is? 10 by 4. 10 by 4? Okay. So 10 by 4. And what we don't know is this down here, right? So we can use, you know, the formula that Bushong uses in the book, but it's a whole lot easier just to take the large dimensions and put them on one side and the small dimensions and put them on the opposite side. And as long as we're comparing the same like things, you know, and by like, I'm not talking about the size as much as I am the measurements, all right? So these vertical measurements is 40 and 5. That's a big, this is a big, this is a little, right? So you've got two big measurements and you've got two little measurements. All right, so what we're going to set this up as is big over big equals little over little. All right, so that means we've got one big that we don't know, and we're just going to put it on bottom. So we're going to say that's X. Now we'll just say X. All right, so we've got another big, and what is our other big? 40, right. So it's 40 over X is equal to, and the things most similar to that, the other vertical is 5, right? So we've got 5 over 10, yeah. No, 5 over, did I work at 10? Yeah, I did, okay, 5 over 10. Okay, so now what do? Cross multiply. So you got 40 times 10 equals 400 is equal to 5x. Divide both sides by 5. Both sides by 5. And what do you have? X is equal to 40. Right? Oh, no. What did I do wrong? The math. The math. Maths are hard. So I just missed it. All right, so now when you get to the registry and all of the questions that you're going to see in registry review books and in the Angelus, which is really just a registry review book, they might give you a rectangular, aperture diaphragm size, opening size. But that's only going to be in one of the answers, right? So even though it looks a little more arduous and difficult than what it necessarily has to be, it's not that complicated. I don't know that I've ever seen one that you actually had to work both of them, right? So if you work it right the first time, preaching to the choir here, then you're not really going to have to work out both dimensions. But just for the sake of argument, let's do it. So if we work out the other dimension, then has our SID changed? No, it has not. So it's still 40, and it's still, we don't know what that is, but what we're going to have is really the same thing here, right? And then our other one was 4. Okay, 4. So now what do? Cross multiply. We have 160 is equal to 5x, and since my brain isn't working today, what is that? So it's gonna be what, 30 something? 32 equals x. All right. Well, I can't see around the corner. I'm looking at that whole screen looks like it's that big. All right, so then let's kind of change it up a little bit and see if what I said proves itself out. If I set it up differently, will it be any different? So let's flip it this way first. All right, so if I have 40 over x is equal to 5 over 10, if I cross multiply, what do I have? 5x equals 400, x equals 80. Does that equal that? Mm-hmm. Yeah, okay. So we know that if we reverse it, then we're gonna get the same thing, right? So what then if we flip it? Well, let's look at that. If we flip the whole thing, we'd have x over 40 is equal to 10 over 5. Cross multiply, we have, oh, wait a minute. Let's see. X over 40 is equal to 10 over 5. Yeah, 400 is equal to 5x. Divide both sides by 5. And what do we have? 80 equals x. Is that the same thing? Mm-hmm. Yeah. Okay. So just keep the things across from each other, and providing you've got a calculator on hand and you don't try to do this out of your head, you're going to get it right. Okay? Big over big, little over little, compare, put across the same type of measurement, vertical, horizontal, vertical to vertical, horizontal to horizontal, big, little, doesn't matter how you set it up. you're gonna get it right. Okay? Now, what happens if I flip just one side of it, though? Five over 10. Now I've got 200 equals 10x. Divide both sides by 10, and x is equal to 20. Does that equal that? The answer is no. Okay, invert one side, bad. Invert both sides, you're still fine. Okay, so calculation of field size. All right, so this has all been about what happens as you expose more tissue to radiation, right? So KVP, or if you change the PE ratio. So what happens, what do we do to create more scatter in the X-ray beam? You expose more tissue, change your KVP, increase your KVP specifically. So if we increase our KVP, what happens to total interactions in the body? Well, they all go down, really, but our PEs go down faster than anything else. So what we get is an increase in total interactions inside the patient's body. If we have no changes in mass, then what we get is, just a lot more penetration through the patient. With changes in mass, with 15% rule, we still have a decrease in absorption in the patient, more penetration through the patient, specifically scatter radiation, right? So scatter, a higher percentage of what we scattered inside the patient is going to penetrate through the patient. So we have increases in the remnant beam, especially if we don't change our mass, and we have a lower percentage of PEs, more penetration, more scatter penetration through the patient. Decreases, everything goes in the opposite direction. If we decrease our KVP, we get more penetration in the patient. We're still going to create a lot of scatter radiation, but that's still, did I just say that backwards? If we decrease our KVP, we're going to have less penetration through the patient. The scatter creation that we do, the scatter that we do create inside of the patient is going to absorb, a lot of it's going to absorb inside the patient. So fewer exit the body, be it what would transmit or scatter radiation in one. All right, so with the increase in KVP, we get an increase in emissions from the tube, emissions from the patient. We get a higher number of, more interactions inside the patient, but more penetration. Patient in image receptor exposure increases, but we get a tremendous amount of scatter. So as we irradiate more tissue with thickness, thickness is usually soft tissue. Soft tissue is full of water. So any kind of tissue that has a lot of water inside of it, you create a lot of scatter radiation, right? So with thickness, we create more scatter radiation. Volume, be it depth or width, we're going to create more scatter radiation. Area is your width, your beam restriction. And then composition depends on what the tissue type is. So if we have an increase in bone, maybe acromegaly or osteopetrosis or something like that, we're going to have more it's still going to scatter, but a lot of that's going to be absorbed inside of the patient. But if we have a loss of stuff like bone, and we have an increase in water, then we're going to create more scatter radiation. So anything that changes the composition to more like water, we're going to create more scatter radiation. And it doesn't have to be from bone to water, it can be from air to water, right? So if a patient takes a pleural effusion, you're going to create a lot of scatter radiation. As opposed to chest x-ray, just a regular chest x-ray, you don't necessarily need a grid for a chest x-ray. We use one most of the time, but you don't necessarily need one. But if you're shooting a patient with a pleural effusion, you really need a grid because it's, chest is full of water in that case. So how does that add to the image? Contrast. All right, so in that it changes the tissue composition. Tissue composition is what gives us our contrast. It's going to affect contrast. The scatter all by itself will affect to some degree, remembering though that the main thing that controls our contrast as far as our machinery goes is our computer algorithm. It's going to compensate for some of that. But again, if you fill the lungs up with fluid, or the pleural cavity up with fluid, your tissue composition is going to change considerably, and your contrast, the appearance of contrast is going to decrease even with your computer algorithm. So it will affect your contrast. Density, remember that's the dicey one. Density really, again, equate exposure here. It will change your tissue density. The difference in tissue composition will change tissue density, but in as much as changing the appearance of the image because of the contrast present, not really. Computer algorithm kind of fixes that. So there's a lot tied up in density. The scatter radiation lays down the layer of density, but it doesn't necessarily mean that you're going to visualize that density. What's going on with the tissue? Do we have a condition that changed the tissue composition? In that case, it's going to change the density. But in as much as the density on the image and the perceived density, it might change your exposure some, right? Also, don't confuse the exposure caused by the scatter radiation to the exposure to the image receptor as being an increase with an increase in tissue thickness, right? So we talked about that a couple of weeks ago, or a couple of lectures ago. As we increase tissue thickness, we get an increase in scatter production, but a lot of that scatter absorbs inside of the patient, so your image receptor exposure, your density goes down, right? Even though you get more scatter, your exposure goes down, right? So sharpness of recorded detail, can it affect sharpness of recorded detail? Yes. Sharpness of recorded detail, just the scatter, no. The thickness can potentially because of OID issues, but the scatter all by itself is not going to affect your sharpness of recorded detail. It's all about visibility functions. Okay, so technical compensation is all about mass. Why not KVP? Because with KVP, if you increase your KVP, you increase scatter, right? So if you increase scatter radiation, you're trying to limit scatter radiation. Those are mutually exclusive. So you use mass, right? So how do you compensate when you're using AECs? That's kind of a trick question. What do you do whenever you're using AECs? Nothing. You do nothing because your AECs compensate for you, right? So if you have an increase in tissue thickness, you shouldn't have to do anything. Your AECs should take care of it. Your AECs are just radiation detectors. They receive the proper amount of radiation, they send the signal over to the timer circuit, discontinue the exposure, and your compensation, you don't have to do anything with it. So that holds true for tissue thickness, but it also holds true for beam limitation. So let's back up just a little bit. Actually, let's reorg it. No, that's not. Okay. All right, any questions on all that? All right, then we're going to start with grids today. And so everything that we've done so far has had to do with scatter creation. Now we're going to concern ourselves with scatter cleanup after it's created. To prevent it from being created, proper KVP, beam restriction, compression possibly. Still going to create scatter radiation, especially if you have soft tissue. So now we've got to clean up what does get scattered. And we use grid primarily for that. There is another thing that I'll talk about when we get to it, but a grid primarily is what you're going to use. So the purpose for a grid is to clean up that scatter radiation. It's developed by Gustav Bucky, and it utilizes alternating strips of lead and radio opaque and radio lucent material. So kind of think of it like, mini blinds, right? Mini blinds, you twist them, and you can block more sun. You open them up, sun gets through. Or a pergola, right? So it's going to block some of the radiations before it makes it to the image receptor. All right, so the dicey thing about grids, and I'm going to turn this off again, is that in order to be effective, what we need to accomplish is we need the grid strips to be parallel to the divergent central ray. All right, we've kind of talked about this in positioning. You probably got a little bit of this in intro last semester. But if the grid strips are radiopaque means you can't see through them very well, right? Metal is radiopaque. Lead is a metal. So in order for the X-ray beam to make it through the pieces of lead, what we have to have is some sort of radiolucent material that the X-ray photons can make it through. Okay? So the tricky thing about it is that if you are off just a little bit in your positioning, be it with the X-ray beam or with the positioning of the grid, then the X-ray photons are going to hit the sides of the grid strip, and they're going to be absorbed, right? So a lot goes into the construction of a grid, and the attempt to make these little strips or these radiolucent areas parallel to the X-ray beam. All right, so a lot of different ways that we can make them to where they'll absorb transmitted X-rays, but transmitted X-rays, but absorb scattered X-rays. All right, so we got scattered X-rays. That will be a transmitted X-ray. We got a scatter X-ray created here, and if it is traveling on a trajectory like that, then our next interspace would be here. Would that X-ray photon make it through the grid? The answer is no. Okay, so first off, we have to have the grid strips parallel to each other and parallel to the central ray. We have really fundamentally two types of grids. One is parallel, and one is what we call focused. All right? So the purpose for the grid is to absorb wide angle scatter, to absorb it before it makes it to the image receptor. So a parallel grid is very simple to create. All they do is they take an interspace material and they sandwich it between two pieces of lead. All right? So you just got alternating pieces of radiolucent material, alternating pieces of lead. So you got lead, radiolucent, lead, radiolucent, and so forth. Interspace material can be made of a number of different things. Plastic is common. Paper used to be common, but the problem with paper is that if blood or body fluids got down inside of the grid, you've seen what happens if you drop a book in water, right? What happens to the pages? They just fill up with water and they're distorted from that point forward. So if we have a situation where the grid gets wet with paper interspace material, that same thing's going to happen inside of the grid strip. Anybody ever seen a retaining wall that after a heavy rain like what we just had, it's just falling down? That's what you call hydrostatic pressure. So the dirt behind the retaining wall, if it wasn't built properly, the dirt behind the retaining wall absorbs a lot of water and it just knocks the retaining wall down. And that's exactly what happens inside of the grids with paper interspace material. So plastic is better, right? You don't have that kind of problem. So the interspace material can be made fundamentally of anything, as long as it's radiolucent, number one, and number two, it doesn't distort whenever it gets wet, if it happens to get wet. But the grid strips are always going to be lead. So it's going to be lead, interspace material, lead, interspace material, lead, interspace material. So how do we make it to where we transmit as much of that as possible while blocking that? Well, we can do a number of different things. All right, so what we can do is we can take the grid strips and we can kind of spread them out. All right, so now we've got, instead of our original grid, we've got grid strips that look more like this. And let's say that this grid is that tall. Okay? Would this X-ray photon now make it through and strike the image receptor? Answer is yeah. So is that effective? It's effective at transmission, but is it effective at absorbing that wide angle X-ray? Answer is no, it's not. Right? So if we have more lead strips in there and these little hallways here are more narrow, does that increase our efficiency? Answer is yeah. Okay. So what if then we've got this grid and we cut it down to this thick? Now would that X-ray photon make it through? The answer is again, yes. Yeah, it would. All right, so what we need is a balance between the thickness of the grid and the length of the grid strips and how close they are together, okay? So we can manipulate that, and if we wanted a thin grid like this, how could we make it to where it would absorb that X-ray photon? Could we do something? Just looking at that, could we do something where it would still allow this X-ray to make it through, but block that one?
Closer together?
What's that?
Closer together?
Very good. What if we added more grid strips? We'll put one right there. Would it block that one? It's getting kind of busy in there. It's kind of tough to see, but would it? Mm-hmm. Answer is yeah. Okay. So what if the height of the grid really wasn't an issue? So we go back to this. What if the height of the grid, the thickness of the grid, really wasn't a problem? Could we again make it where our grid strips are taller and block that X-ray photon? And again, the answer is yes. In both of those cases, what did we add? In a word, what did we add in both of those cases? What are the strips made out of? Lead. It's lead. Okay, so anytime you add more lead to a grid, it becomes more effective. Well, how are you going to, add lead? In one or two ways fundamentally. Either you're going to make them longer, essentially, or you're going to put more of them closer together. Will those grid strips absorb X-ray photons that hit them? I missed completely. Hit it right on the end. Would it? Yeah, it would. So would it make it more effective if I were to take just the grid strip, this grid strip, and say I've got a thin grid again, and just make it thicker? Mm-hmm. It would, right? But what kind of problems would you have then? If these lead grid strips are really, really thick, what are you going to see?
Not a whole lot coming through.
You're going to see a lot of grid strips, right? Is that ideal? No. So what you want is you want your grid strips to be as thin as possible and spaced such that it blocks these, but it allows more of these. If you have big, fat, thick grid strips, then you're going to have grid lines. Grid lines are just an artifact, and they make your image look awful. Okay, so what we have then is grid ratio. Grid ratio is the measure of how effective a grid is. So it's a comparison between the thickness of the interspace material. So how thick is it between here and here, and the height of the grid strip. So grid ratio is height of the grid strip over the thickness of the interspace materials. So what we want is a grid ratio. Most of your grid ratios in the hospital are going to be like 10-to-1 grid ratio. That's going to have more lead than an 8-to-1 grid ratio. All right. So when we're talking about grid ratio, we're talking about the height of the grid strip divided by the distance in between them. And the higher the number, the more lead we have in our grid. Okay, so 16-to-1 grid ratio has a lot of lead in it. Okay, so if it's got a lot of lead in it, it's got a lot of what we call cleanup. It cleans up a lot of scatter radiation. So if we go from an 8-to-1 to a 10-to-1, we clean up more scatter radiation. We'll go from 10-to-1 to 16-to-1, and there's some steps in between. You can go to a 10-to-1 or 12-to-1. When you go to a 16-to-1, then you're going to clean up more scatter radiation. Okay? But the downside is that with each one of these, you're going to absorb more of the transmitted X-ray beam as well. So you're going to absorb scatter radiation, that's good, but you're also going to absorb some of the X-rays that you want. All right? Now, your index number, your calculation of your index number, compilation is just a compilation of X-ray photons that hit the image receptor. So let's say you made a perfect X-ray without a grid. Okay? So you made technically is perfect X-ray. Your technique was perfect. Right? So your index number turned out perfect. You add a grid, and the grid absorbs nothing. Let's say in this hypothetical world, it doesn't absorb any of these, but it absorbs these. So it absorbs a wide angle scatter, but allows every transmitted X-ray photon to pass through. Is that going to change your index number? If you didn't phototime, you set a technique, would that change your index number? Index number takes all the photons that hit the image receptor, and that's what it, the index number includes all of those photons, scattered and transmitted. So would that change, if we absorb these, would that change your index number? And the answer is yeah, it would, dramatically, right? Okay, so if we change from an 8-to-1 to a 10-to-1, would it absorb more? The answer is yeah. If we went from 10-to-1 to a 16-to-1, would it absorb more? The answer is yeah. The more lead we add, the higher the grid ratio, the more cleanup we have, and the lower our index number. So again, you shot the perfect X-ray, perfect technique on this image, and then you added a grid. Your index number is going to indicate that you did what? Overexposed patient? Underexposed patients, right? So, what would you have to do? Increase something, right? What are you going to increase? Mass. Why not KVP? More scatter. Right. You increase your KVP, you're going to create more scatter radiation. Create more scatter radiation, kind of defeats the purpose in a way, but at the same time, let me show you a strange phenomenon that happens. Okay, so if you look on page 302, what you see there is Bucky factor, right? So the Bucky factor is how much of a change in mass you need as you change your grid. All right, so on the far left, it says no grid, and then 5-to-1, 8-to-1, 12-to-1, 16-to-1, right? So your Bucky factor is the number that you would multiply your mass by in order to calculate what your technique change should be with each one of those grids. So if at 70 kVp you made an X-ray, and then with no grid, say your technique was, I don't know, 80 kVp at 20 mass. So with a 5-to-1 grid, what would you need? Multiply your mass times your Bucky factor. What would you need?
2.
It'd be 2 times, so you would need 40.
Yeah.
Right, you'd need 40 mass. So with 8-to-1, you'd need 60. And with 12-to-1, you'd need, what would it, 70? 16-to-1 would be 8, right? So that would be your technique, your technical compensation in mass. Now, notice that it's got 3 different kVps there. So you got 70 kVp, 90 kVp, and 120 kVp. As we increase kVp, we create more. The purpose for a grid is to absorb, scatter. Right. So now what you need to look at is the 120 kVp with a 5-to-1 grid. If you shot the, let's say we now instead of using 70 kVp, we use 120 kVp. Let's say we use 120 kVp at 20 mass, and we incorporate a 5-to-1 grid. What's our Bucky factor? What was it at 70? It's 2. What is it at 120? 3. Why? Why? It's a critical thinking question of the day. Why is the Bucky factor higher at 120 kVp? Because you create more scatter. And the grid, the purpose for the grid is to clean up scatter, right? So as kVp increases, the grid becomes more effective, right? So could you increase your kVp to compensate for a grid, for grid use? The answer is yeah, but the calculation of what you would need to change your technique to becomes much more convoluted, becomes much more difficult. So we use mass. Most of the time we're using 80, 85, 90 kVp. So in most of your test questions, we're going to be using, the standard 80 kVp. And our Bucky factors are really going to be 8-to-1 is going to be 3, 12-to-1 is going to be 3.5, 16-to-1 is going to be 4, something like that. So first test, you're going to have the Bucky factor given to you, but the Bucky factor is the amount of change in technique you need, specifically mass, for when you use a grid. Okay, Bucky factor, that's all it is. How much of a change in mass do you need? All right. All right, so a grid designed to transmit only X-rays traveling a straight path from the tube to the image receptor. Scatter is absorbed in the radiopaque strip. The radiopaque strip specifically is lead. The radiolucent portion can be made of almost anything. So grid effectiveness. We've got 2 different measures of grid effectiveness, grid ratio being the most significant. So grid ratio is the height of the lead strip. So the taller the strips, the harder it is for the even shallow angle scatter radiation to make it through it. And I like to use this analogy. When I was a kid, I had an older brother, and I grew up in this house that was built in the 50s. And back then, they loved a hallway. And we had this hallway in our house. It was probably, 60, 75 feet long. And every Christmas we get these little dart guns, and they were kind of the precursor to Nerf guns. They didn't have foam arrows. It was hard plastic arrow with a suction cup on it. It would put an eye out. And he'd get at one end of this hallway, and I'd get at the other end of the hallway, and we'd just start blasting away at each other. You know, it was just a spring. So you took this thing, you crammed it down in, compressed the spring, pulled the trigger, and the dart would come out. And if I was at one end of the hallway in our bedroom, and he was at the other end of the hallway in Mom and Dad's bedroom, it was a hard shot, right? Because any deviation, and you'd hit the wall. But we'd start to advance on each other until we were shooting from 10 feet away, and it wasn't so hard. Okay, kind of the same thing here. If your lead strips are tall and those little hallways, those radiolucent spaces are narrow and they're tall, then it's very difficult for any deviation of that X-ray photon to make it through that. So tall grids, harder for the X-ray photons to get through, absorb more scattered radiation. So the thickness of the strip, we talked about that. The thicker the strip, the more lead it has and the more X-rays that it absorbs. And in that, though, what we see are grid strips on our image. We don't want that. So really the better way to increase grid effectiveness, the problem with the tall strips is that we've got a thick grid. And with a thick grid, what we've got is an increase in OID. The increase in OID, we lose sharpness of recorded detail, right? So the better way to do it would be to narrow those hallways, make them shorter, make them more narrow, and that would also increase grid effectiveness. So grid ratio is the height of the strip divided by the distance in between those strips. So it's the thickness of the interspace material. What you're going to have a tendency to do is make your grid ratio the height of the strip divided by the thickness of the strip. It's not the thickness of the strip, it's the thickness of that hallway. Okay, it's how wide is that interspace material. So height of the strip divided by the distance in between the strips, the thickness of the interspace material. So all that we talked about, the higher ratio of the grid, the more effective it is, the more scatter it cleans up, the more exposure you're going to lose, though, it absorbs more radiation. All right, so height of the strip, thickness of the interspace material. So the lead strips are the dark parts, and then you've got the interspace material in between. Grid frequency is just that. Grid frequency is how many grid strips you're going to have in a given distance. So if you have grid frequency that is, 120 grid lines per millimeter, per centimeter, whatever measurement, per inch, that's going to have a higher frequency than 80. Okay, so the higher the number, the higher the frequency. And grid frequency was just kind of like an afterthought for a while. All right, so it didn't really become a prominent. It didn't take a prominent place in construction of grids until we moved into CR. All right, so have you ever taken a picture off of a computer screen or a TV screen or something like that? You ever seen the appearance? You get these funny little colors and you get these wavy lines, right? Everybody know what I'm talking about? It's what you call moire artifact. It's M-O-I-R-R-E, moire artifact. Also referred to as aliasing artifact. So if you have two different things, especially electronic, two different things that have similar reconstruction patterns, you're going to have that. So when you're looking at a TV, you're out shopping for a TV, what are you looking for? You look for bit depth, right? How many colors can you see? But what's the other thing that you look for? Pixels, resolution. It's a matrix. So what you're looking for is a large matrix, small pixels in a large matrix, right? So big numbers, right? So when we changed from screens to CR, with screens and films, we didn't have anything electronic that could cause any kind of problems like what I'm talking about. moire artifact. But when we went to CR, then what we had was we've got a grid, and the grid has distinctive strips in it, and the pattern of those grid strips were very similar to the reader pattern of the CR system, which is very similar to, in theory anyway, to the display pattern on your TV, right? So what we had were two very similar read patterns trying to line up with each other. And every x-ray that we created, we left what we called that moire artifact on. If we were using a grid, that moire artifact would show up. So what they had to do was make that dissimilar. They couldn't really do anything with CR reader for reasons we'll talk about later on, but to change the reader would be to change the resolution on the x-ray. Didn't want to do that. So what they did was they took our x-ray grids, which had relatively long hallways, they cut them in half, all right, this way, kind of like filleted them. They took them, and instead of having big, thick strips on, wide hallways, basically what they did was they shuffled them together like so that now what we've got is same grid ratio with a much higher grid frequency. So the number of strips went from 5 and however many inches that would be to 10 in about the same distance. Okay? Moire artifact went away. So grid frequency became more important. How that affected text, really it didn't in technique formulation, but this is the way it did. Who has put their marker on the image receptor and then pushed the image receptor into the table bucky or the wall bucky? Where's your marker go?
Top.
Sometimes it gets eaten by the bucky, right? Anybody had that happen? No? Because you put it on tabletop, put it on patient, right? Well, the reason people are doing that now is because with that smaller, thinner grid, the distance between the grid and the bottom of the table bucky and in all honesty, the thickness of the image receptor changed as well. The distance or the space that you used to have to put your marker onto the image receptor has narrowed, all right? So now the bucky will eat your marker. So everybody's putting, the marker either on the patient or on the outside of the image receptor, or outside of on the tabletop or on the bucky rather than inside of the bucky on the image receptor. So grid frequency. We made a thinner grid with more strips. The effectiveness remained the same. Grid ratio roughly remained the same by increasing grid frequency. All right. Any questions?